Howdy, folks. So for this review, we're going to take an approach at learning and recognizing each functional group and coming up with molecules based on its formula. So to start, we're going to take an alcohol and this formula, C5H10O2. So go ahead and pause. So in whatever way you want to construct it, with whatever subgroups you want, build an alcohol with this formula and then give the name. And see if you can come up with an isomer of it. Come up with a second molecule that has this formula and give it a name. And then unpause, come on back, and we'll go through several. Alright, if you're back, well, let's look at some of the possibilities. What is an alcohol? It is an ROH. So that is, there's some carbon with an OH, and that carbon generally doesn't have any other oxygens or nitrogens or anything. It can have some carbons and hydrogens, and then those can have more, and being that I have two oxygens, well, I can't put them on the same carbon, really. I guess that would be a diol. You could get away with that. But I've got 5 carbons. However, I want to spread 5 carbons out. I then need an OH, and I have a second oxygen, so, another OH. I've got 5 carbons, I've got 2 alcohols, so I've used my 2 oxygens, I've used 2 hydrogens, I have 8 left. 1, 2, 3, 4, 5, 6, 7, 8. I need a 9th and I need a 10th. Well, hey, what if instead of hydrogens there to fill in those carbon bonds, I just make a double bond? If that's the case, we can rewrite it a little nicer. Double bond OH. To a carbon that goes to 2 carbons, and one of those goes to an OH. And so here's one possible form. How would we name this one? Well, I need the longest chain that includes my alcohols. And 1, 2, 3, 4 carbons. And we want our OH to be as low a number as possible, so it'll be from the left. I'll get it at 1. Otherwise, the other OH would be the second. If I went from the top down, it'd be 2 and 4. This time it's 1 and 3. I have a methyl. And so it is 4 carbons long. It is a bute. It is a double bond. It is a bute 3-ene. It is a diol at the 1 and the 4 position. And it has a 2-methyl. 2-methyl bute 3-ene 1,4 diol. Well, this methyl, what if I just had put it here? What if this had been a bond there and this had gone to a hydrogen? It would have made a slightly different chain. I would have had a molecule that was carbon up to an OH, to a carbon, double bond to another carbon. This one would go to OH. Very similar. In this case, I've got 1, 2, 3, 4, 5 carbons is my longest chain that has all my functional groups. And, well, our numbering this time from either direction, our OH is number 2. And if we count, so 1, 2, 3, 4, or 1, 2, 3, 4. No matter what, they're 2 and 4. Well, what breaks the tie? Double bond. If our OHs are the same numbers, we want our next thing to be the lowest. And so we're actually going to number 1, 2, 3, 4, 5. So this one's a pent. It's a pentene at the 1 position this time. And it's a 2,4 diol. And I realize I made a slight mistake if you're watching the video before. That's a 1,3 earlier. My apologies. Glad we caught that quick. A lower version here, this is another isomer. It still has the same number of every atom. We just moved that methyl to make a longer chain. Well, other things we could move, what about that double bond? What if I go back and say, hey, instead of connecting those two, what if I'd connected these two in the middle instead? Double check, all my carbons have 4 bonds. Count up my hydrogens, 1, 2, 3, 4, 5, 6, 7, 8 on the carbons, a 9th and a 10th on my oxygens. So here's another form. Maybe you came up with this one. What would that look like? 2 carbons, we'd have an OH, a 3rd carbon double bonded to a 4th that goes to an OH and a methyl. And so we'd say, what's our longest chain? Well, 1, 2, 3, 4, 5. We didn't change our chain this time. We just moved where the double bond was located. And so it's 5 long again. We need to come up with numbering. Well, again, it's going to be a 2 and a 4 for my alcohols from either side, but 1, 2, my double bond will be the tiebreaker again. This is going to be a pent. This time 2-ene. 2,4-diol. And this one, now we can follow the chain in and out. This one is cis. Our first ones weren't because it was on the end. 2 of the groups were identical. They were both hydrogen. So there was no differentiating cis and trans when the 2 groups on the same carbon are the same. But now we had different groups down here. We had a methyl, we had an OH, we had a hydrogen, and we had whatever this 2-carbon OH chain would be. And so now we had to deal with cis and trans. Other ways you could make this, what if instead of connecting adjacent carbons, what if we connected over here? So now you could have a carbon with an OH. That carbon goes down, over, those connect. This one goes to an OH and to a CH3. So this CH3, which we'll just draw in as a methyl. So clean this up, make it a little nicer. This also gives us the same formula. Well, this one is 1, 2, 3, 4 in a ring. So this is a cyclobute. They're all single bonds. It's cyclobutane. It has OHs. Well, they're going to be, we get to choose which of them is carbon's number 1. The other is going to be 3 as we go around. So whether we go here to here or here to there, it's going to be a 1 and 3. So we get that methyl as low as it can be. That's the tiebreaker. And so this will be 1, 2, 3. And it doesn't actually matter which one's 2. There's not going to be any other numbers on 2 and 4. So it's only the 1 and the 3 that make a difference here. Cyclobutane, 1,3-diol, and it has a 1-methyl. Well, as we saw up above, we can move a methyl and make a longer chain, so we could also use all 5 of those carbons in a ring and put OHs on them. So what if I put them adjacent? Here's a 5-atom ring. So 5 carbons. If you do the hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So again, same formula, but this time this is a cyclopent. They're all single bonded, so pentan, and 1,2-diol. You can move the OHs around and have a 1,3. There's a lot of possibilities for how to put this together. This isn't at all of them. This is just the ones that have 2 alcohols. You could also have an ethoxy or a methoxy with 1 alcohol. And so you could have 4 carbons, an oxygen to the 5th carbon, put my OH here, Well, let's move it. Let's put the OH here. And a double bond. 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, and my 10th. 10 hydrogens. If this is the case, well, the longest chain are these 4. That oxygen interrupts, so that last carbon on the end isn't part of the chain. This is part of a subgroup. This is a 1-carbon ether, so this is a meth, then oxy for ether subgroup. Number 1, number 2, number 3, number 4. We want our functional group, the OH, to be as low as possible. So this is a bute. It's at position 2, a double bond. Butene. It's at position 1, an alcohol. It's got a methoxy at position 4. And that double bond is trans, as drawn. So here's a way we could have an alcohol, and also happen to have a subgroup included that contains the second oxygen. So there's a variety of possibilities. There are more for the alcohol. Let's move on to our next functional group. So again, C5H10O2. Using kind of what we talked about through the alcohol, go ahead and pause here. Try and come up with 2 or 3 different aldehydes and give the names for them. All right, if you're back, well, what's it mean to be an aldehyde? Aldehyde must have that carbon double bond oxygen, that carbon go to a hydrogen. That is what it takes to be an aldehyde. You must be at the end of the chain having that double bond oxygen. That R group can be carbons and the stuff. It can even be a hydrogen. You can have a methanol. But that's not terribly common. Formic or formaldehyde, we don't like to use a lot of it. It's pretty deadly, and that's the common name, industrial name for methanol. But we need that structure. So if I'm going to have a carbon double bond oxygen, I then can go, well, here's carbon 2. Here's a 3rd carbon. Here's a 4th carbon. Here's a 5th carbon. I need some more. Let's try that. Does this work? 1, 2, 3, 4, 5, 6, 7, 8. Well, that's all my possible positions, and I've only used 8 of my 10 hydrogens. That doesn't work. The problem is the dialdehyde. If I had 2 open spaces there, hey, I could put in more hydrogens. That'd give me 10, but then I'm short in oxygen. But there's ways we can include oxygens. We can have an oxygen go to a carbon. We can make our subgroup ethers. When you make that double bond, you use up an extra position off a carbon. And so you prevent it from being able to have hydrogens there. To get this H10, we can't have dialdehydes. And so we're going to have to come up with various shapes that will have these subgroup ethers. In this case, what would this look like? Double bond OH to a carbon, to 2 methyls, to an oxygen, to a methyl. Longest carbon chain, doesn't matter left or right, it's going to be 3. So our longest carbon chain is actually 3. We don't have 2 methyls off that end carbon. That's just part of the longest chain. We have 1 methyl here, and I have a methoxy up above. And so 3 carbons long is a propanal, and it has at 1, 2, it'll have a 2-methoxy and a 2-methyl. Which one's first? Well, M and M, E and E, T and T, H and H, O versus Y. O comes first, so methoxy. So 2-methoxy, 2-methyl propanal. So here's one way we could build the molecule. Same idea, I have my aldehyde. And I could just do all carbons in a line, put in our oxygen in there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, this is working. We can't have the dialdehyde, but I can definitely have adjustable ethoxy, methoxy type groups. And so I've got a double bond, show the hydrogen, 2, 3, 4, O, boom. In this case, carbon 1, 2, 3, 4. It is a 4-methoxy butanal. There's no reason we couldn't move that subgroup. And so you could also have a 3-methoxy butanal. You could have a 2-methoxy butanal. And additionally, there's no reason you have to have them be methoxys. What if we had, and then we went O for the remaining two. So 1, 2, 3, and then subgroup 4, 5. Our hydrogens, there's 1 to start with. 2, 3, 4, 5, 6, 7, 8, 9, 10. Still works. In this case, it's a propanal. And on the third position, there's a 3-ethoxy. And you could make a 2-ethoxy. There's a few other variants here, but to fit our formula restrictions, this is kind of how we have to do it. It isn't possible to have a dial and have 10 hydrogens on the 5 carbons. And so we have to come up with some other structure. This is fairly common. Subgroup ethers definitely could just add extra oxygens to your formula, but we don't really consider them the functional group of the molecule unless they're the only thing. And so if we're looking for an aldehyde, make an aldehyde. Anything else you need for oxygens, see if you can make a dialdehyde or if you need to use methoxys and the like. Well, after aldehyde was a ketone. So again, C5H10O2. See what ketones you can come up with. Try and draw 2, name them, and then come on back. All right, if you're back, what is it to be a ketone? It is R to a carbon double bond oxygen to an R. And they must be carbons. Specifically, these R groups have to be carbons. If one of them was a hydrogen, you would have an aldehyde. And so I must have a carbon, carbon, carbon with a double bond on it. We'll have a second oxygen, but a lot like aldehydes, if you tried, you'll find you can't have a diketone. It's still 2 double bonds to oxygen on 5 carbons. It doesn't matter whether they're on the outside or inside, the available remaining spots are only 8. We can't get all 10 hydrogens. So I'm definitely going to have some kind of ether methoxy again. So let's just do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Carbon, carbon double bond oxygen, carbon, oxygen, carbon, carbon. For this one, longest chain is 3. The other carbons are part of the what will be an ethoxy subgroup. So I have 3, and well, from either side, my ketone's at number 2, so I'll put my subgroup as low as possible. this is going to end up being a 3-ethoxy. Sorry, not a 3. This is going to end up being a 1-ethoxy. Prop for 3 carbons. Propan for single bonded carbons. 2-one. So it's a 1-ethoxy propan 2-one. And we can change the lengths of things. We can make it a methoxy with the ketone here. We could make it a methoxy with the ketone here. We can't move it one closer because then I'd have an ester. If we tried to do put the double bond here, at first glance, you're like, oh, I can just keep moving that double bond oxygen around, but this would be an ester group. As soon as those oxygens are sharing that carbon, that's now a new functional group. So that doesn't work. And I can't put the ketone on the end because that would be an aldehyde. So that doesn't work. On this 4-carbon chain, there's really just those 2 positions. And so, for naming them, well, they're 4 carbons, so it's going to be a bute. They're all single bonded, so it's a butane. In terms of numbering, we want to hit our ketone as quick as possible, so 1, 2, 3, 4. The ketone has to be reached as quick as we can, but on this next one, well, that'll be from this side. So in both cases, this is going to be a butane 2-one. But effectively, we just swapped which side our methoxy was on. And so up here, this is a 4-methoxy, and down below, it's a 1-methoxy butane 2-one. Really, you can imagine that we just have this same shape, and we took the methoxy that was over here, and we said, hey, I'm going to go and put you over here. All we did was move it around. So here's a couple varieties of ketone we can make. You could have a few other positions, but ketones are a bit more restrictive in the way they have to be assembled. So there's ketones, aldehydes, and alcohols. Now let's try it with a carboxylic acid. C5H10O2. Try and come up with at least 2. Find their names, and then unpause. Alright, so what's a carboxylic acid? R double bond oxygen OH. And so I've got to have a carbon, double bond oxygen OH. Well, that's all my oxygens already, and I've got 4 more carbons. Think about my hydrogens. 1's already there. 2, 3, 4, 5, 6, 7, 8, 9, 10. Sweet. No tricks, no ethoxys or methoxys this time. The formula works for putting down a functional group, making a chain. So this is 5 long. This would be a pentanoic acid. And it has to be at carbon 1 because it's always on the end of the chain, which means we can just adjust the chain. So 2, 3, 4, let's put a methyl here. Or we could say, hey, I've got my carboxylic acid, 2, 3. Let's put 2 methyls there. Well, that changes our carbon length, but our numbering is pretty straightforward because it has to be 1, 2, 3, 4. It's got to be 1, 2, and then pick something to be 3. The others are going to be subgroups. So here's a methyl, there's some methyls. We've got a 3-methyl butanoic acid. And over here we have a 2,2-dimethyl propanoic acid. All right, name that one real quick. If you unpaused here, this is 4 long and it has a methyl, but it was just one of our other versions of butanoic acid. This time it's a 1,2. So this is a 2-methyl butanoic acid. And there are not really that many other versions of carboxylic acid. So when you're filled with hydrogens, you don't have much option but to just move around methyls a little bit. In terms of carboxylic acids, there we go. Ester. C5H10O2. Go ahead and pause, try to draw 2, name them, and come back and check. All right, if you're back, what is an ester? R, carbon, double bond, oxygen, O, some other R group. And so at minimum, I've got a carbon to a carbon, double bond, oxygen, oxygen, carbon. Just to lay down the start of the ester, I've used 3 of my carbons. I only have 2 more. Let's put 1 on each end for fun. There we go. Well, think about hydrogens. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Excellent. We have the right amount of hydrogens. So what is this one? This is 3 carbons, double bond oxygen, O, 2 carbons. Well, we name the single bonded oxygen side first as if it was a subgroup. It is 2 carbons long, so it is an F-ill. We then put a space and we name the double bonded oxygen side as the main group. And so this one is 3 carbons long, so it is a propan. We tell the carbon-carbon on this side. So only main chains get the AN-EN type treatment. And so this is a propan, and then it's an ester, so O8. Ethyl propanoate. And we could do things like move carbons around. And so I could take this carbon here, I could move it over there. If we did that, there'd be 1 more hydrogen on the end. But that's still 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All we did was just extend the chain. And shrink the chain on the single bonded oxygen side. And so you could have a methyl butan O8. You could shift carbons to other places. And so you could have this one is a methyl for the single bonded oxygen side. And be very careful. When folks look at this, I occasionally will see people go, oh, it's isopropyl. But there's this carbon. This is carbon 1. 2, 3. Right? That's not an isopropanoate because you can't have that center carbon have the functional group. This is a 1, 2, 3. This is a 2-methyl propanoate. So don't forget that there's that carbon underneath the double bond oxygen, and that's always carbon 1. We additionally could have a short chain on one side and a longer chain on the other. Let's talk about those isopropyls. In this case, I can. The first carbon of the single bonded oxygen side is part of the isopropyl. And so that's actually something we can do. We can call this one isopropyl. And then the other side is just 2 carbons, ethanoate. Side note, and won't do it on tests, when it's 2 carbons, when you have an ethanoate, the common name is acetate. Acete groups is the old name for 2 carbon components that attach to stuff like this, make these esters. This comes from vinegar, acetic acid. So isopropyl acetate, ethyl acetate, methyl acetate. If you ever see acetate, what it means is that you've got an ethanoate component of your ester. We see this for acetyl-CoA and things like that in biology and medicine. Like acetyl is a very common thing biology does. It's a product of breaking down fats and other things. So just in case you run into it, acetate is an ethanoate. In terms of our various esters, you can continue to move methyls around, but more or less, this is the majority of the structures for it. And so in terms of a little bit of practice of what is the functional group, can I figure out how to build it from a formula? What is the variety of ways that I can build it? And can I find the names for those varieties? Here was a little bit of practice in that regard.